Hello, young people. We are on our third video, still talking about systems, but now we're talking about the size of systems, the scale of systems, and the stability of systems. We are introduced to our hydrosphere, our atmosphere, our biosphere, and our geosphere. Those are portions of the system that's called Earth. Earth's pretty big, depending on what field of study you're in. If you're an astrobiologist or an astrophysicist, Earth's pretty tiny because you're looking at the whole universe. That's a giant system. It's the biggest system we know of. But we can get smaller and smaller and smaller. There's the universe. There's the solar system that fits into the universe. There's the Earth that fits into the solar system. We're getting smaller. It's like Russian nesting dolls. And we can keep going. We can keep going, getting smaller and smaller. Within the Earth, we could look at a desert as a system, or an ocean as a system, or maybe a lake as a system. Or maybe we're urban planners and we're looking at a city as a system, or an apartment building as a system, or maybe a bus as a system. See, we're getting smaller. Russian nesting dolls are getting smaller and smaller. I could look at an individual mineral inside a rock as a system, or a cell, a single cell in my body, all the way down to a single atom could be considered a system. So I hope you understand systems in science pardon me, can range from impossibly small to impossibly large. Not impossibly, but unimaginably. We use systems to look at change. We look at change within systems and how systems affect one another and how events affect systems. I have this system of a body. If I had an event of stubbing my toe, that would affect the system of my body. It would cause all kinds of effects. I stub my toe. It triggers pain in nerves, which causes a change in my brain. If it hurts bad enough, that change in my brain, it might actually make my eyes water. Right? So stubbing my toe can make my eyes water if it's a significant enough event. And the significance of an event depends on the scale of that event. What do I mean by that? By scale, I mean we need to compare the size of the event to the size of the system the event is happening in. I'm going to use the human body as a model for this explanation here. If I'm cooking dinner, I'm boiling some noodles on the stove, making spaghetti, and a little bit of that boiling water splashes, just a droplet of boiling hot water splashes onto my arm. It hurts just a teeny tiny bit. It hurts pretty quick, goes away pretty quick. It doesn't really do any harm to my system, my body, my skin. I don't even need to look at the whole body as a system. I could just look at my skin as a system. But that one little droplet of boiling water doesn't do much. The size of the event compared to the size of the system, it's just a really small event. However, when I'm going to drain the noodles, if I slip and spill the entire pot of boiling water on my skin, that's a huge event, and I might have to go to the hospital if I get that much boiling water on me. Might have to get skin grafts and stuff. Big event, because the size of the event compared to the size of the system it's just a bigger event compared to the size of the system. So that's what we mean when we say scale. We're comparing the size of one thing to the size of another thing. Um, we can also talk about scale and time. We're going to talk about the time of an event. Um, we can have events within a system that are incredibly fast. Radioactive decay happens like that. Um, a lightning strike is an event in a system. It affects the system and it happens in less than 1 second. We could go a little bit longer, slightly longer scale. How about a landslide? A landslide might take place over a few minutes, or some of the slower moving ones even over a couple hours. It's an event taking place in a system, right? We can go even longer. How about a volcano erupting? That can take place over hours to days. So our scale of time is another thing that we need to look at. We can go to really slow events too. For example, over the last 20,000 years, sea level has changed about 4 inches, if I remember correctly. Don't hold me to that number. Pretty gradual. Takes place over thousands of years, tens of thousands of years. Or we could go even longer than that. Plate tectonics, continental drift, takes place over hundreds of millions of years. So our time scale for events within a system is another way of looking at the significance of an event. And then finally, the last little thing about systems is stability. Some systems are incredibly stable. They will not change very quickly. For example, the conditions of the rocks on the moon don't weather because there's no atmosphere on the moon. It's a very stable system. It's been the same way for billions of years. But you can also have extremely dynamic systems, so stable systems like the moon, or dynamic systems where they're very complex and easy to change. And in a dynamic system, something like, say, the atmosphere, a change in one location can cause a change in another location. Take, for example, El Nino from our first video. El Nino is a very complex phenomenon, but a change in the Pacific Ocean can cause us to have a warmer winter in continental North America. Finally, systems can either be open or they can be closed. And simply, an open system means that matter and energy can flow into and out of the system. And a closed system is just that. It's closed. Matter doesn't get in or out. Energy doesn't get in or out. We can generally think of the Earth as a closed system, although the energy thing's a little bit dicey because energy comes in every day from the sun and energy leaves every day, but it's about the same amount coming in and going out every day, so we can just think of the Earth as a closed system. But something like the ocean is absolutely an open system. Water can evaporate from the ocean to the atmosphere, and you have matter that's leaving the ocean and going to the atmosphere. All right, that is size, scale, and stability of systems. It's our third video. We've got one more Unit 1 video coming up about using evidence in science. We'll see you there.